What you're looking at here is a very old Yamaha action model. One of the dead giveaways, obviously, is that this whip-in is very old-fashioned, kind of like what you find on the old Kawais and many older European pianos. No longer original equipment in Yamahas, but that's what was there. Now let's notice a couple of things about this action model. One, the capstan is adjustable, so I can try out all sorts of different settings. The knuckle itself is made of wood, and it has a screw on top, so actually the knuckle can be moved around as well. So I could try that out to see what would happen to regulation as well as to down weight. It's regulated for about 46 millimeters of blow and a complete 10 millimeters of dip at the front end of the key. And I've used this interesting little gauge here. Looks like a tuning fork made out of plexiglass, made for Kawai, designed by our friend Ray Chandler. And it's like a fork, so it's tapered. When I put it in here, I can get a quick sense of key dip at the very end of the key, and it's 10 millimeters. Also on this action model, I have an adjustable capstan screw at the front here so that I can define dip exactly without any sponging effect from punchings. Alright, having said all that, the action goes through let off and drop and a little bit more, so it has the usual parameters in place, the visuals in place for a properly regulated action. And with the aftertouch gauge in place, it press it down right to what kind of gets to that point of let off and then stops, and with a little more push there, it drops through. So aftertouch is 1.25 millimeters. Now, you can see how slow the key drops down. What I mean to say is relatively slow, right? I mean, that's what we've been talking about anyway, the sort of balancing thing, which is really what downweight is. Now I'm going to take this capstan screw and I'm going to move it towards the front by 2 or 3 millimeters. And just doing that one thing, let's see how fast the hammer moves up. Okay. I'm not really concerned about changes to geometry. I just want to point. So that's about 3 millimeters or so. Oh, here we go. Bang. Bang. Really fast. So, I mean, I'm just guessing here, I'd take lead out. That's not the right one. The point is it won't need as much lead. Maybe this one. That's more like it. So, instantly, we can see that lead removal is in the works, or a much heavier hammer would be able to work on an action like this. So the mechanical advantage has been seriously increased just by this one little change in there. So let's look at the lesson involved here. Shortening any output arm increases the mechanical advantage, meaning a heavier hammer can be used, but requires more dip. Now I'll put the aftertouch gauge in there and we'll see that we probably don't have it, or we shouldn't have it, okay? So, shortening an output arm. Well, isn't that an output arm? The back end of the key is an output arm, correct? All right, that's that lesson for output arms there, and that's a big one. That's a big lesson. So what do we have for aftertouch? Okay, here we go. I can't get it through. I cannot get it through aftertouch no matter how hard I push. So that means more dip would be required. But we had it set at 10, and clearly I'm going to need more than that. I could also see it, as you probably could, so I'm going to take some out. just beginning to drop through a little more. Okay, there we go. We're back to having the aftertouch we had earlier. But in order to do that, we've had to increase the dip a certain amount, which I'm not that interested in right now, but we can see that the gauge doesn't fit tightly anymore. Probably requires another, maybe a blue punching or a little bit more, I would even think, in order for that. So dip had to increase. So that's what the lesson was. Shortening an output arm, in this case the key back, increase the mechanical advantage, bang, no doubt there, but also required more dip at the key end. Right, so I made a couple of changes. Going back to our lesson sheet, we see that shortening any input arm decreases the mechanical advantage but requires less dip. So input arms are different than output arms, obviously. The front of the key is an input arm. The whipping from here to here is an input arm, and the little shank dimension from here to here is the third input arm. Shortening any input arm decreases the mechanical advantage but requires less dip. Well, is that the case? In practice, well, my movable knuckle began at 17 millimeters in the last segment. Now it's at 16.2. And I adjusted the jack forward to follow that. Capstan is back in its original position. So what's happened? Well, let's see. We had 50 grams down. Now we need 55. Okay, so obviously the mechanical advantage has decreased. And a lighter hammer would be called for, or else more key leads to make up the difference. Obviously, mechanical advantage is not as good as it was. Now the key dip, which earlier was 10, let's go through the cycle here. There we go. Now watch the back end of the key and also the back check especially. You'll see that after it goes through let off and drop. Drop is extra long, by the way, to make it obvious. So it drops, and then watch this. You can see the back of the key and the back check continue. Okay, so that's one of the visuals for aftertouch. And it turns out that what's required out here, the front end of the key, where it was 10, is like 9.75 or 9.8 or so millimeters of dip required. So, like the lesson sheet said, mechanical advantage decreases, and the dip required also decreases.